So we've already described number theory as being sort of the core of crypto systems. Crypto systems are any systems that involve encryption, security systems. They're all over the internet. Anytime you log into an account, there's some sort of encryption process that takes place. So we need to get a good foundation in some of the properties or theorems of divisibility. And here we're going to say that a, b, and c are just some integers where a is not 0. So you can already tell that a is going to be the divisor. Then the following three properties hold. If a divides b, that means that b is divisible by a. And if a divides c, that means c is divisible by a. Then we can conclude that a also divides their sum. So let's think about property 1 intuitively first and see how this relates to what we already know. So for property 1, we can give an example of this, and we can say that, for instance, 2 does divide 6, and 2 does divide 12. So 6 divided by 2 is 3, that's an integer. 12 divided by 2 is 6, that's an integer. Now remember, these are just true or false statements. This does not mean what is 6 divided by 2. This just is the statement 2 divides 6. That can either be true or false. In this case, they're both true. So if 2 divides 6 and 2 divides 12, well, one way we could write this is we can say that 6 divided by 2 is equal to 3, which is analogous to saying 6 is equal to 3 times 2. Over here, we can say that 12 divided by 2 is equal to 6, which is analogous to saying 12 is equal to 6 times 2. Now, if we were to add these two numbers together, if we were to add 6 and 12 together, and we were to attempt to divide that by 2, then one thing we could do here is that we have now these identities or these other ways of writing 6 and of writing 12. And so that allows me to now say that this is equal to, well, 6 is 3 times 2, 12 is 6 times 2, and we're dividing that whole thing by 2. Okay, so how do we know for sure that that's divisible by 2? Well, we already know that both of these quantities, 6 and 12, are divisible by 2, which just means they can be written as a multiple of 2. And since both of these two terms contain 2, I can actually factor that out and write this as 2 times quantity 3 plus 6. And divided by 2, well, we already know that if we multiply something by 2 and then divide by 2, that those operations effectively cancel each other out. So 3 plus 6, which is equal to 9, is the result of taking 6 plus 12 and trying to divide it by 2. So this is sort of our intuitive proof or our intuitive proof by example of why if one number divides two different quantities, why it will also divide their sum. Now we can formalize this. We want to formalize this. We want to say that suppose A divides B and A divides C. Now we want to establish that A divides B plus C. So what can we do here? Well, this means that if A divides B, that B is some integer multiple of A. Okay, so C is just some element of the integers. That B divided by A equals C. Now here we can also say that C is some, I gotta be careful here. I should probably say C, maybe I'll go ahead and get rid of C here and use a different letter in there. Maybe we'll say F, we'll say D, where D is some integer. Now A divides C, which means C is some multiple of A. So I'll say C is equal to F times A, and A is just some integer. And what we're saying here is that C divided by A is equal to some integer F. Now we construct the sum of these two numbers. So if we take B plus C, well, since B is equal to D times A, C is equal to F times A, I can substitute those in and replace them. So writing B plus C is the same thing as saying D times A plus F times A. And now I can say that if I take B plus C and I divide it by A, that's equal to, Well, b plus c is equal to dA plus FA divided by A. And once again, just like in our numerical example, we can factor out an A and write this as D plus F divided by A. Cancel those out, and I get D plus F as the result. Now, since D is an integer and F is an integer, their sum is also going to be an integer. There's no way to get decimals when you add together two integers. That's the bottom line. So this concludes our proof. You'll often see this little box here to say that that concludes the proof, that that's the rationale for why this always works. Now there are a couple of more properties, and this is usually the way we go about proving new number theory properties, is by some sort of process of substitution. Maybe start off with an example and see why it's true, and then use symbols to show why it's true. So if A divides B, then A divides B times C for all integers C. Now this one's a little bit easier to view, because if A divides B, that means that B divided by A is some integer. We'll call this integer D. So that's an integer. So A divides B is a true statement. Okay, well, if I now try to form B times C divided by A, well, how do I know that that's going to produce an integer? Well, we just said that B divided by A is some integer, so I'm going to break this up into B divided by A times C. B divided by A is equal to D, and D is an integer and C is an integer. So if I multiply two integers, that is itself an integer. And so this kind of just says that if B is divisible by A, another way we could interpret this is B is equal to D times A, and so we could replace B with D times A, and that means we'll have D times A over A, and the A's will cancel out, and we'll be left with D times C. So there are a couple of important properties here that I'll point out, and these are called axioms. Axioms are things that are assumed truths. There's no way to prove them. No way to prove them. And here are a couple of the most important axioms that I want you to think about going forward. One is that if A is an integer and B is an integer, then A plus B is also an integer. Now we can reason through that and say, well, if you take whole numbers and you add them together, you're going to get whole numbers. But this is not something that we can absolutely prove with certainty. And two, if A is an integer and B is an integer, then so is their product. And these are two assumed truths. Now you can probably say, well, duh, these are things that we know that if you add together two whole numbers, it's not going to suddenly become non-whole, but there's just no way to prove this in particular. These are what we call the closure properties. And that just means, by closure, we just mean that the sum of two integers is closed under addition. And that word closed just says that you produce another integer, that you don't leave the set of integers at all. You're enclosed in that set. And same thing with multiplication. Now here's another interesting one. If A divides B and B divides C, then A divides C. And you might recognize this from relations as the transitive property. So let's go ahead and finalize this by showing that number 3 is also a true statement. Okay, so as an example, let's say 2 divides 6. We know that's a true statement. If 6 divides 18, that's a true statement. Then can we conclude that 2 divides 18? Well, yes, 2 does go into 18 a total of 9 times. You could remove 9 copies of 2 from 18, and this is a true statement. But this is just for these particular three numbers that we've selected. So we want to be able to make this general. So suppose A divides B and B divides C. We want to conclude that A divides C. But before we do that, we're going to come up with some definitions of what we mean by these things. So if A divides B, that means that B is equal to some multiple of A. And so D is going to be some integer. If B divides C, that means C is equal to some other multiple of the integer B. It can't be D again, because then we'd be saying that the factors are the same, or that the division produces the same integer each time. And F is some integer. Okay, well, how do we construct this idea that A divides C? Well, if we took C divided by A, we can do that. That's no problem. We just don't know if A will evenly divide C. What we can do now is we can make some substitutions. So we know that C is equal to F times B is equal to F times B, and we know that by this statement right here. Now here's where divisibility gets a little interesting, because if we were to try to use this first identity to replace A, we would be replacing A, and I'm just going to go ahead and write this for a second. We would be replacing A with B divided by D. Now, this is a problematic statement because in our original theorem, we indicated that only A is not equal to 0. So what happens here if B is equal to 0? Well, if B is equal to 0, then we have a division by 0 error. If D is 0, we have the same problem, but just in the denominator. So instead of trying to create additional divisibility problems, we already know that A is not equal to 0, so we're going to leave A in there exactly as it is. We're just going to leave it as F times B over A. Now, how do we get that A somehow to cancel out? That's really what we're trying to do here. I'm going to make one more substitution, and that's going to be that B is equal to D times A. I'm not going to be able to create any problems in the numerator because that's just a multiplication of things, and we can have 0 in the numerator. So what I'm going to do here is I'm going to say this is equal to F times B, where B is equal to D times A. And if I divide that by A, and I know that A is not equal to 0, I can see that those two elements cancel out. And I'm left with the product F times D, neither of which is guaranteed to be non-zero. One of these could be 0, or they could both be 0 in some cases. Then this clearly is an element of the integers by the closure property of multiplication that we established up top, right up here in the axioms. So we just have to be careful when we're doing division. If something we know is not equal to 0, it can appear in the denominator without any issues. But if something could potentially be 0, we just have to be really cautious not to potentially introduce a divide by 0 error. So this is where number theory can be a little tricky per se, and the way we handle that is by just making sure that we do not introduce something that could possibly be 0 in the denominator. And again, if we replaced A with B over D, then we face the issue of somebody saying, hey, wait a minute, but what if one of those things is 0, then you get a divide by 0 error. So this is the way we avoid it, by never introducing 0 into a denominator.